And lastly, we're going to look at the specifics of catalysts. Early on with the collision theory, we said that they react without being consumed and they speed the reaction up. When we were looking at mechanisms, we understood that they would collide. They would collide in an early step, they would be created in a later step, and in doing so, they would give us maybe a different path for the reaction. If we can't speed up a reaction for some reason using concentration or temperature, sometimes catalyst or catalysis is the only option. Sometimes catalysts are used just because they are the cheapest or most efficient option. And the nice thing with catalysts, because they're not consumed, in theory, they can be used over and over. So even in a medical, an industrial, a chemical application, we can use that again later. What they do is provide an alternative mechanism for the reaction that gives us a rate determining step that has a lower activation energy. That means that they somehow give us new and different steps that make that energy less. Overall, we often graph it just as a where are we starting, where are we ending, what hill do we have to get over. In a simple start to end reaction profile, the activation energy is lowered. The reality of it is that they have to give us maybe one or two different steps. It's not always more steps, but it has to be different steps that don't total the same high activation energy. It may be a series of more steps, it may be fewer steps, but the key is that they don't go as high or require as much energy in turning reactants into products. In terms of collision theory, the key isn't that they collide faster or they collide more often. The collisions that they provide or help facilitate are more likely to be successful, maybe by changing the shape of the molecule, maybe by opening up a certain part of the molecule where the collision needs to occur, but they could orientate the molecule, or orient is how I like to say it, which is grammatically incorrect, so that the collisions occur more successfully. When we're doing this, a lot of times we might create new or different intermediates that somehow stick to the reactant. It could be with the covalent bond. It could be by bonding to the surface. It could be by bonding to hydrogen ions. So there's different specific types of catalysis, but really we don't need to understand the mechanics of why something works that way, as long as we do understand that it's not always the same situation. Some catalysts would be homogeneous with the reaction, a whole bunch of gases reacting, and we put another gas in. Very often they're heterogeneous. We have an aqueous or gaseous solution, and we might have a solid as our catalyst. All of that works because it somehow gives us a pathway where the bond that is temporarily created with our catalyst and some molecule makes the reaction a little bit easier. Very important in biology are catalysts that we call enzymes, and they increase the rate of biochemical reactions. And sometimes we think about them as obviously being totally necessary. Reactions wouldn't occur without the right enzymes. So when we take this this graph and kind of turn it on its side, we see less energy required here, less energy required here. And when we apply that to a Maxwell-Boltzmann distribution, one thing that's key is that we are making a pathway with more successful collisions. More often than not, that means that the molecules don't have to be moving as fast in order to do that. The bond breaking events are more likely either because of shape or because of strength of bonds in the new pathway. So a higher percentage are successfully colliding. In both cases, our activation energy corresponds to a lower energy collision as being a successful collision.